Hey everyone, in this video we're going to be doing an example where we're going to use implicit differentiation to find the derivative of an equation that's defined implicitly but also includes some of our other functions, namely exponential and trig functions. So again, the process for implicit differentiation, we're going to take the derivative of both sides with respect to x, and then we're going to solve the resulting equation for dy over dx. So here's my example. E to the y power times the cosine of x is equal to x plus 1. And again, this is defined implicitly. It's an equation that's defined in terms of x and y. So the first thing, we're going to take the derivative with respect to x of both sides of this equation. So d over dx, and we'll take that of both sides. So taking the derivative with respect to x, we can use any of our other rules that we have already established. So on the left-hand side of this equation, I have two parts that are being multiplied together. So I'm actually going to need to use the product rule on this left-hand side. So the product rule, we're going to do the first times the derivative of the second. So e to the y power stays the same. And then we're going to take the derivative of the cosine of x. And then to that, we're going to add the derivative of the first part. So the derivative of e to the y. And then we'll multiply that by the second part, which is the cosine of x. On the right-hand side of this equation, I'm taking the derivative of a polynomial that just has x's in it. So this is our normal power rule. So the derivative of x is just 1. The derivative of 1 is just 0. So we just get 1. Okay, going back to the left-hand side, we have e to the y power. The derivative with respect to x of cosine, so this derivative is negative sine of x. And in our second term, here we're taking the derivative with respect to x of e to the y power. And again, just as a reminder, because the variable in this term is y, after we take the derivative of this, we also need to include dy over dx. So the derivative of the exponential just stays the same. So this is still just e to the y, but now I need to also include dy over dx. And this is being multiplied by the cosine of x. So there we go. We took the derivative of everything. And now we want to solve this equation for dy over dx. So we want to isolate this. So the first thing I'm going to do is this negative, I can bring it out front. And I'm actually going to add this term to both sides. So what I end up with, and doing a little bit of rewriting here, so I have ey times the cosine of x times dy over dx. And then adding that term to both sides, we have 1 plus e to the y times the sine of x. And then the last step, we have some multiplication here. So to get my dy over dx all by itself, we're going to divide both sides by e to the y and by cosine of x. So our final answer here, we get 1 plus e to the y times the sine of x, and then this is divided by e to the y times the cosine of x. And again, our notation dy over dx, that represents our derivative. So the derivative of y with respect to x is this equation here. And now that we were able to find that, we could use this equation to find the slope of the tangent line, to find the instantaneous rate of change, or a number of other things. But that's how we use implicit differentiation to find the derivative of equations that contain exponential or trig functions.